Thanks, and thanks for the introduction. This is joint work with Hamza and Omar. Let me first start with explaining this first word of the title, because we might not talk about the same thing, all of us. What do we mean by the certified algorithm? So there's a quantity that we want to compute, some quantity of interest. It will something be in quantum many-body physics. And what we want is we want upper and lower bounds on this quantity. So you give an algorithm, the algorithm outputs two numbers, an upper and a lower bound. And it will be a very general algorithm. So we will cover loads of instances, including very hard problems, which are complexity theoretically known to be hard. But we are not afraid, because even if we will probably not get convergence guarantees for these large classes, we can still get a posteriori error bounds. So you run your algorithm, you have an upper and a lower bound, so you have an error interval. So afterwards you know how well you performed. And then you can still hope that maybe once you have this framework that covers many instances, you can specialize the algorithm, look at certain cases, and prove stronger results on the convergence. So this is the thing we're looking for in this talk. And now we have this idea of what algorithm types we are interested in. Let's talk about the problem. So we are in the problem that probably has come up quite a few times in this conference of many-body systems. We look at, in particular, translation invariant and infinite spin lattices. Translation invariant and infinite is not necessarily for everything we do in our work, but we specialize to these cases because we believe these are the most interesting formulations of our results. And what we look at is a local Hamiltonian. I think we've seen it a few times. A local Hamiltonian is a sum of local terms. And in the case of the notation I use, I will usually assume it's two local, so no interactions between spins that are further than one side apart. But it will not really matter for the formalism in the end. And the work is about thermal equilibrium states. And when we say thermal equilibrium states, we mean actually both ground states and Gibbs states. And maybe I'll just start talking about the possibly more familiar version of finite systems. They're a ground state you just know as the ground state vector, the lowest energy eigenvector of the Hamiltonian. And observables, which are a state applied into an observable, are given by just the expectation value of this operator A in the state psi 0. And similarly for thermal states, there is this Gibbs states formula. We just take any observable and here's this explicit formula, plug in the Hamiltonian and get the value. This is not always sufficient to look at this description to treat infinite systems. And I don't want to be too technical, but I also want to emphasize that there's a technical difference. For infinite systems, you still talk about states, things mapping observables to their expectation values. But rather than giving explicit formulas, you kind of define the constraints on these states. So the ground state is given by this thing. This should hold for some version of all operators A. I skip the technicality of what A can be taken from, but kind of all observables. And if you want to specialize to finite systems, think of this like if you have an energy jump operator that takes you from a lower to higher energy level, this constraint tells you there cannot be no population in the excited states, because otherwise this inequality would be invalid. And the so-called KMS states, which are the infinite system generalization of thermal states, are given by this condition on the state, which is something like if you commute your operators, you get something like an imaginary time evolution. Also, this is to be taken with a grain of salt. This imaginary time evolution does actually not really exist in infinite systems. And this is also the reason why we will later actually circumvent this definition and replace it by a different one. But just this spirit is still important. Instead of having an explicit formula, we have constraints on the states we care about in this treatment of thermodynamics in infinite systems. Okay, so next is what do we want to compute? The quantity we want to compute is just an observable. So we want an algorithm that takes any observable O and outputs the value. And now we already come to the first problem. Beforehand, we had for finite systems these explicit formulas, and for infinite systems, just constraints. So it's not quite clear, will there be only one state if I take an infinite system in the thermal or ground state? And in fact, it's not true. It can happen, and this is related to something like phase transitions, that there are several possible values for an observable at a fixed temperature and for a fixed Hamiltonian. There's still a lot of interesting scenarios where this will not happen. If you have some proof there's no phase transition, this usually also means at the same time this interval is just a single point. But it can happen in general. And it's also related, what happens if you just take your finite system and take a limit then? So you just cut off your system and then make it bigger. Then it might happen that you just get 1 point out of this interval. And it can happen that if you change the boundary condition, you can obtain different points in this interval. This is how the finite system description relates to the infinite system description. It's not unique to go from a local Hamiltonian finite system to the infinite system. Okay. So this is what we want to compute. We want an algorithm that gives upper and lower bounds on this quantity. And as you can now see, it will actually not be upper and lower bounds on this number. It will be upper and lower bounds on the interval. And if it's a number, then you get a precise error interval for the number. Okay. This slide will be kind of the summary of the whole talk in very quick, including how we construct these algorithms and what we infer from them. So what we do is we introduce a hierarchy of convex relaxation. If you don't know what this is, it will come later again, which means we will take our constraints on these states we're interested in and we will relax them. So we'll obtain a bigger set of states instead the ones as the ones from the definition. And that means when we then maximize over this set of states, we get upper and lower bounds because we optimize over more states. And the key goal of this is to like formulate this in a way, the conditions from before were in somehow infinite states. We want to formulate this in a way that you can treat it with an algorithm. So everything should be finite dimensional and finitely many constraints. Yeah, and as I said, then you just minimize and maximize and you get lower and upper bounds for free. So what are the kind of results when you construct this? The first thing I just said, it is this version of certified algorithm that we're looking for automatically. And a further result, this is not trivial from the hierarchy, but we can also prove that it actually converges. So you get arbitrarily close to this interval if you just wait long enough. This so far comes without a convergence speed. Many people might not be happy if there's no convergence speed. It's okay, but it still actually tells you something. Because if you just run this hierarchy long enough, you will converge. And if you just talk about the sort of weakest notion of a positive complexity result, that is decidability, you can decide whether quantity is below or above some certain threshold. I will formulate this sort of problem that we treat a little bit more careful later. This can actually already be treated by any sort of convergence, and that's one of our results coming from the construction of the algorithm. And then, if you don't like decidability and want something more polynomial time, we don't have that much, but we have a little bit. We specialize, as I said in the beginning, to a certain subset of the problem where we say we assume our Hamiltonian will be commuting, and then either 1D at any finite temperature or 2D at high temperature, we can prove that we get a polynomial time algorithm out of this same framework. And finally, we have numerical results. I will just show a few pretty pictures later. They also maybe not amazing, but they actually show some usefulness in some cases. And I would say it's kind of interesting that we have like in one slide and for one framework, something ranging from decidability to numerical results. So that's quite, maybe quite unusual actually. Okay, so let's look a bit into how the construction looks like. I will talk a little bit more about the construction, but a little bit less about the following kind of tiny proofs that prove all these tiny convergence things. So how does the general thing look like? What we want is the constraints in a like feasible algorithmic form. What we formulate is a convex relaxation, and we optimize over sort of moment matrices that are sometimes called, or just marginals. So we just optimize over states that give us the observables on a subalgebra, just on like finite subsystems. We give for each observable the expectation values, and this can just be written in a matrix. And then we put some constraints on top of it. One is it's normalized. As we know, quantum states are normalized. So we want our relaxation to be as well. Then we want it to be positive, but we have to relax this. We can't just say this comes from a positive state on the whole infinite system. We can just impose it's positive. It gives positive values on all positive operators up to a certain locality. So this is one way how we relax the original problem. And then we ask for something like translation invariance, because we start only from translation invariant formulations. And there again, we can't impose this for all operators, but we say like, as long as the operator is a little bit included in the interior, we can wiggle it around a bit left and right, and this is sort of the amount of translation invariance we can impose given the amount of observables that we define in the level of the hierarchy. And as you can see, there's kind of a parameter how big the hierarchy becomes. If I make L bigger, I get more constraints. These are the constraints, and then what we do, I said it before, we actually just want the value of an observable, so the actual problem we solve is we maximize the value of the observable in this bigger set of states by optimizing over all these functionals that fulfill the constraints. This is relatively standard. I mean, you've probably seen a bunch of talks doing a similar thing. But the big question is now, how do we force these states to be somewhat an approximation of the thermal state? And as I already said, this is a bit problematic. This is one constraint you can put. It's a linear constraint in the moment matrix. That's nice. It's even linear in A and B. That's also nice. You can just pick a basis of A and B and impose this constraint. You pick the basis obviously just from the finite dimensional algebra, because you can't do more in this level. But then you run into trouble because you actually realize you have this imaginary time evolution, and that's not local anymore. So we can basically not write down this constraint. We could approximate it. That would come with other difficulties, but I won't talk too much about where you actually run into bigger trouble. We kind of give up here. The only exception where we wouldn't give up is if the Hamiltonian is commuting, you can actually do it, because then the locality of B by this time evolution, imaginary time evolution, would just be increased by 1. So you could actually write the constraint down, and we actually do this for the case of the commuting Hamiltonians. But for now, let's replace this constraint. If you look into the literature on infinite spin systems, you see they've proven equivalent conditions, and one of them is the so-called energy-entropy balance inequality. It is something that is formulated with some commutators, and first let's notice they're only local operators now. The commutator increases the locality of A, but just by an extra side, not by infinitely much. So if you pick A from a slightly smaller subalgebra, everything is just defined on local observables, and these are anyway just local observables. So you can write down everything in terms of just these moment matrices in your hierarchy. And furthermore, one problem is it's not linear in A, so you would have to write it down for all A in this subalgebra. It's finite dimensional, but it's an infinite set, so that would be too much. And what we do because of that is we introduce a sort of matrix version. Can we somehow reduce this again to be only imposed on a basis of operators, not on all operators in the subalgebra? And this expression here, we take some matrices, which basically takes the sort of these expressions and the conjugated one from the previous slide, as well as this matrix, and we make everything a matrix version. So we pick a basis of our subalgebra and write down these values. And then we kind of replace this logarithm by this kind of relative entropy by a matrix relative entropy. It might not be clear at all right now that this is the same thing, but we prove it is the same thing. So when you have a KMS state, we use this definition of KMS states and the techniques from there to prove that the matrix version still holds. So this is a relaxation. If you write this down, it's valid. It will give upper and lower bounds. In the other direction, it's not necessary for the relaxation to be valid, but for later on to prove stuff, it's very convenient to say, actually, if you have the matrix version, you can also derive the scalar inequalities from before. So it's kind of equivalent for our purposes. Okay, so this gives us basically the finite construction of our thermal states, the constraints from before, plus this matrix relative entropy, and then we optimize. In the case of ground states, this is actually easy to replace. You just pick beta at infinity. This actually means you scrap the left-hand side and say 0 is smaller equal. Then you actually reduce to the condition that was already known for ground states. So for ground states, this condition always looked like this. Just this term is positive semi-definite. But we kind of obtain it again as a special case for the thermal states. Okay, so it's a convex relaxation because the matrix relative entropy is a concave function, convex function. And then this is maybe not quite enough. I mean, there's like vague results that convex problems are easy to treat, but we can make it even a bit better. We can say it's all an SDP, except for the last quantity. It contains a logarithm, okay, but for logarithms, there are further approximations which are SDPs by themselves. So you can make another approximation, and then it's entirely an SDP. So all your theoretical computer science results will hold on the efficiency of solving SDPs. That's actually work by Fauzi et al. On approximating the matrix logarithm. Yeah, and just denote then the resulting values from this hierarchy as P min L, P max L. Okay, So this is a construction, and now let's see what we can do with it. First thing, I mean, I don't go into much detail, but I mentioned it before already. It converges. So you have this interval of values you want to approximate. The lower bounds converge from below to the lower bound of the interval, and the upper bounds can converge from above. Even if you don't know how fast, again. But as I said, this is okay. We have very hard instances in this problem. We don't expect there to be a convergence speed in such generality. And as I said again, even though you don't know how fast, it's certified. So afterwards, you know how well you did when you see the result. Okay, and this is kind of the formulation of this decidability problem that we said we can solve with this. So you have to put some promise. The promise is not so much about a gap here because we don't care about runtime in the decidability, but it's important to say you have this interval, and either the whole interval is above a threshold or the whole interval is below a threshold. If that's the case, then you can decide which one is true. This is our result that we have. This is actually like it's immediate from the convergence, really. You have to do some technicalities on numerical accuracy or so, but otherwise it's immediate, basically. And why is this interesting? I mean, it's just a decidability result. The interesting thing is that the same thing has been proven to be wrong. Almost. Because there was a result by Johannes Bausch, Toby Cubitt, and James Watson that showed that the equilibrium observable problem, basically in this definition, is undecidable, but the difference was they did not use these star algebras. They used a concrete Hamiltonian, took the Gibbs state, and then took a limit. Or only for this value, it was shown that it's undecidable in the same. They proved kind of for this concrete instance the same promise, but in this case, it would be undecidable. So it's very close to a too hard problem. But in this case, in this formulation, this problem is decidable. I already mentioned before, I don't go into much detail on this slide, but there's a sort of stronger a quantitative convergence result resulting in a polytime algorithm for commuting Hamiltonians. You need one of these cases where it's known that algorithms exist in these regimes in 1D and in 2D at high temperature. But then you get like the hierarchy converges exponentially fast, which means you have a polytime algorithm or a quasi-polytime algorithm. The techniques we use in here are kind of standard in the many-body literature. You first like extract from your hierarchy some Gibbs states, and then you use decay of correlations, indistinguishability, which are known exactly in these regimes, and then you get the result. Finally, I promised some pretty pictures. So as I said, like you have this very theoretical guarantee. You know that it's certified, so even if you don't have guarantees, you can do something useful with it. These are cases for which we don't have many proofs. We're restricted to 1D numerics. It's kind of hard to do more than 1D practically on your computer. There's, for one thing, the transverse field Ising model at infinite temperature in the ground state, and at zero temperature, where you have a phase transition, so you might expect things to get computationally hard, and it is true. Like it works way worse close to the ground state, but it gives you bound everywhere where you like far away from the phase transition and get pretty good convergence on both sides, here in the degenerate and here in the non-degenerate regime. And at the ground state, you still get, well, some bounds, but they converge way slower. On the other side, we have a kind of boring case. There's like not much happening here, but we also certify there's not much happening here. It's like a finite temperature. Okay, you have no finite temperatures in 1D, so you couldn't really look at thermal phase transitions, but you still, like in a sort of trivial model, you also get bounds that certify that you're in this zero magnetization regime. All right, so just to summarize quickly what we all did in this work. We introduced convex and later on semi-definite relaxations for the equilibrium observable values, so ground states and thermal states, and in very much generality, so for all temperatures and all dimensions. These are inspired by what you get from reading these algebra books, and take their definitions and reformulate them into computationally feasible constraints. And we have like upper and lower bounds, and we can, using these upper and lower bounds and the convergence proof, some decidability results that was actually not known before about this general thermal states. And in particular scenarios, you can even prove efficient algorithms. Yeah, and we have some numerical results, so you can try to tweak these hierarchies, change some, add some constraints, prove more stuff. So there's still a lot to do, and I thank you for your attention.
Thank you very much. Are there questions? Exactly. If you have any, please come to the middle.
So with the transverse field Ising model there, it was as though the bounds that you had were able to signal a phase transition. Is that right? To what extent have you explored that possibility?
So we cannot really certify the point of the phase transition.
Yeah.
Because there's kind of an issue that in this case you really see it converges really fast, but theoretically it guarantees very little.
Yes.
Because you don't know whether the interval was actually non-zero or whether you converge. This is something we do not know.
Okay.
And you see, like, okay, you see the phase transition heuristically.
Yes.
But theoretically, you can do very little
You
with
can't
it
say anything
to
concrete.
like localize it. Yeah.
Yeah. Okay. And can you go back? Can you clarify again how your result differs from the result from Toby and
Sure. Maybe I go back to one of the very early slides because I defined the problem here once. So, okay, maybe this formula is interesting. This is kind of what Toby did. They had a explicit construction for the local Hamiltonian terms, and then you take this and you cut it off at the system size lambda. And then you take the limit. And this gives you just one of the values in this interval. And which one this is undecidable. But in our definition, what you would kind of expect is probably if I actually know at least an explicit point in their proof where I can say, okay, if I add an Hamiltonian term to the boundary here, then their proof at least breaks down. So their proof that this non-halting Turing machine is mapped to the zero observable value will not longer hold if I change the boundary. They even explicitly use the boundary in some sense. So that would mean I can change this and then expect not to get 0, but 1 anymore. And in this case, it would mean for this particular Hamiltonian, there's actually a boundary condition that yields 0 and one that yields 1. So this will be an interval from 0 to 1.
So intuitively, is it somehow the difference, like when people take thermodynamic limits, it matters which
yeah.
Is that sort of where this is coming from?
Yeah.
Yeah.
And also kind of tells you it's important in these results that you consider the boundary condition. Otherwise, it's a lot harder to formulate this undecidability result.
Okay. All right, thanks.
Hi, thanks for the nice talk. I guess it's also related to the previous question, but so for the last slide with the transverse field Ising model, I guess we can see a very sharp curve at the transition point that you're supposed to have. I'm just wondering if that's just supposed to be the thermodynamic limit behavior, or if you're like drawing it as a curve you actually get with your algorithm.
So the curves, the blue and
yeah, the black line is what.
So the black line is the thermodynamic limit. This problem is solved.
Oh, that's the limit.
Sorry, the black line is not our numerics. The black line is the analytical solution.
Oh, okay. I thought it could be like the lower bound or something.
Oh no, sorry. No, the lower bound is below and the upper bound is above. It's like the quantities is in this. This is like the quantity from -1 to 1.
I see.
And the blue and the gray lines are upper and lower bounds.
Okay. So what you're saying by what you mean by saying that it captures the phase transition is the fact that like it goes to 0, like roughly.
Yeah, it gets steeper. Let's say this, like, but the blue line is not very conclusive yet. But you have to look at the blue line. This is all you get of the algorithm, and the black line is really a phase transition.
Thank you so much. Cool.
Hi, thanks for the really nice talk. I was just wondering, can you say anything about like the general conditions on which you can say something about the convergence speed of the algorithm? Maybe I missed this when you were talking about it.
You mean in the fully general result or in the commuting Hamiltonian result?
In the fully general result.
And they're like the conditions are holds for all temperatures, for all lattice dimensions. Yeah.
Oh, sorry, but can you say anything like what are the general conditions for the convergence? Like when can you say something about the speed of the convergence?
We have proven only this case. In the general result, it's really it uses a weak star subsequence, so there's no convergence speed at all. And here only commuting Hamiltonian, 1D finite, any finite temperature, 2D high temperature. There we have the convergence speed.
Okay, thank you.
Okay.
Can I ask 2 questions, actually? So one is just clarifying about this difference between my old results and yours. So if so we could prove undecidability. I think. I mean, we did it with open boundary conditions in that paper, but I think you could also prove with periodic or with fixed boundary conditions. In your case, the reason this doesn't, if you took this limit of this sequence, the infinite sequence we construct, and go to the C-star algebra framework, is the point that your results, you can't see the boundary anymore, so the results would have to hold for all whatever boundary condition I choose. Is that one way of interpreting it? And so you get these intervals which are coming from the value expectation of this value should be, because you're only allowed to look on the compact regions with compact support, you can't see the boundary conditions, so you get this interval because in some sense, intuitively, it's for all boundary conditions. Is that?
Yes, that's pretty much. So you said you used open boundary conditions.
Yeah.
You actually did talk about a boundary term first and then pushed it into the Hamiltonian
Yes.
to say open boundary conditions.
Yeah.
You could probably do it for each type of boundary condition.
Right, good. Okay.
Yeah. But then it's our point is like our quantity will always be for all boundary
Oh,
conditions,
thanks.
the interval.
Great. Okay, good.
Yeah.
Understood. The other thing I wanted to ask is a different question. So you you can only do things for commuting because, I mean, then you get things stay local in the, is that right? Or you use the fact that when you have commuting Hamiltonians, the imaginary time evolution, you keep kind of local operators?
So there are two things. The proof for the commuting case uses actually the skip state, this KMS state type condition that you can actually only formulate into your hierarchy. So we use this in the proof rather because for the other versions we use CEB in the hierarchy.
Good.
And generally you could also prove maybe something with CEB conditions, but we haven't done
I was going to ask, no, just for the KMS conditions, could you potentially extend it if you make some assumption about the some kind of clustering or some, so where that the imaginary time evolution, a type of a dissipative type Lieb-Robinson behavior, so that you still have quasi-locality even without commutativity and push a bit further?
Yes, that's actually, if you look at the plenary talk from yesterday on the learning Hamiltonians, they did also actually the KMS condition, but they had an explicit epsilon upper and lower bound. So we need from analytic results an epsilon that we can put there. As you say, if you have a dissipative Lieb-Robinson bound, then you can put it. And as you like increase the size and make the epsilon smaller, you should still converge. But just as long as we don't have this, we can't formulate it in full generality. But that was the issue. Yeah,
Thanks.
Exactly.
One last quick question, please.
I'll try to be quick. On this result that's on the slides now, what prevents you from going more than 2D?
This is an excellent question. A technicality, basically, in our proof. And like from what we know of literature, obviously, like in 3D, it should work as well in any higher dimension for high temperature. It's really just something we kind of have to trade off a boundary term coming from this hierarchy construction. And this boundary term grows exponentially linearly in 2D because the boundary is just linear. And in 3D, it will grow e to the squared size of the system, but the decay just goes linearly in the system length.
So it scales with the size of the boundary?
It scales with the size of the boundary, yeah.
Exponentially in the size of the boundary, I guess.
Exactly, yeah. And then we have the corresponding trade-off exponentially in the size of the linear size of the system. So in the higher dimension, it didn't trade off. But it's purely a technicality. Maybe if you give a smarter proof, you can come around it. There's actually any regimes where you know convergence results, it's interesting to try to prove them in this framework. But we just didn't manage for higher dimension technically.
Thank you. Maybe we can talk about this later.
Yeah, sure.
This is an excellent keyword. So like if you have any more questions, you should do this over coffee. And then let's us take the opportunity not to only thank again all the speakers of the session, but also the people making it possible to run this session as smoothly as they do. So yeah, let's give them